Hi, this is Duke Data Plus Team 6, and the title of our project is using automated interactional synchrony to predict complex behaviors. My name is Damilola Oshoinka, and my team members include Jessica Tang and Jesper Hu. Our project manager is Daniel Parr, and our project lead is Dr. Gianna. A brief introduction of our project. Our main project's goal is to actually create a unique data set that can be used to describe the different dynamics of features present in synchronous interaction. And this data set can actually be used to predict trust in negotiations and also create early diagnosis tests for different social disorders like autism. Our major objectives was to actually propose a pre-processing steps to extract audio features and also to actually extract the audio features using MATLAB codes and to plot a parallelogram that will depict the correlation between the different measures of synchrony. I'm going to pass it on to Jessica to talk about the methods we employed in this project.
Yeah, so first we wanted to deal with the audio feature extraction, which we wanted to do to understand synchrony between two interacting individuals. So we proposed to extract two auditory features, which are pitch and loudness. So for pitch, we implemented two pre-processing steps, center clipping and low pass filtering. And you can see the before and after of implementing these pre-processing steps in the visualization at the bottom of the first column for one participant. And then we wanted to compare two different pitch estimation methods. So those are Cepstrum method and autocorrelation method. And you can see the differences between those when we calculated the pitch estimations. And the autocorrelation method seems to produce a cleaner signal. And for loudness, we didn't implement any pre-processing steps, but we still wanted to compare two different extraction methods. And those are extracting decibels from the audio file and extracting power through finding the average squared value of amplitude within a window of time.
Yep, so now we'll move on to video feature extraction. And so we essentially try to extract action unit strength, which are anatomically distinct sets of facial muscle movements that categorize facial expression. And we did this through a neural network-based model called OpenFace, which tries to plot out the facial landmarks on your face. And then so after we obtain these strengths, we run through two rounds of smoothing. The first round is a confidence-based weighted average, and then the second one is an algorithm called matching pursuit, which tries to denoise the signal.
So for the results, in our pitch extraction methods, we found that the correlation between the Cepstrum method and autocorrelation method is weak. We found that it had an R value of 0.33, and you can see the scatter plot that shows this at the top of the third column.
Yeah, and then we also conducted a correlation comparison between all of the synchrony measures on each of the action units. And then we can in general see that Pearson and Spearman are pretty similar. And we can also see that the derivative dynamic time warping produces pretty similar results across all AUs, which is a good indication that it's a good measure of synchrony.
In conclusion, we were able to successfully define the pre-processing steps for extracting the audio features, and we actually wrote the code and successfully extracted these features. We hope that our project will aid future researchers to better understand interactional synchrony as regards audio and video features. Thank you.